Hello, how's everybody doing? Can everybody hear me okay? You just got out of bed? This is an excellent time to just get out of bed. Hey, Vanshika. There again, Aisha. Nice to see everybody. We're probably just going to wait a couple minutes, or maybe like a minute, as usual. Hey, Blah. Hey, Zara. Just for a few other people to show up. Hey, Tilly. Okay. Let me share the presentation with you guys. Hey, Fassy. OCR lad. I like that. Hi, Rebecca. Hello, everyone. Let's. Oh, interesting. Okay. All right. Can everybody see the presentation? How long is this? About 45 minutes. This will be, so the first, this should be made for everybody. There's not really much that other people won't be involved in. Yeah, it should be 45 minutes though. So what we're going to do is mostly look at electrophilic addition. Is everybody able to see sort of like the full screen? Yeah, awesome. Hello, T-Boy. All right, let's get started. So the aim of today is to, firstly, we want to recall, yes, it's recorded, Jalach. We want to recall sort of essential vocab about reactions in general. And then we're going to want to have a look at the reaction mechanism for electrophilic addition. And then we're going to think about our Markovnikov rules involving electrophilic addition. You may not have called it Markovnikov rules, but that is what we're going to be looking at. All right, so here are your spec points if you are AQA. The only thing we're not doing from these today is the bromine test for unsaturation. So our real focus is on the reaction mechanism itself. Here's your basically the only spec point for OCR because it doesn't go into much detail. Your man Markovnikov, yep, an amazing guy. And for EdXL, we're just going to be looking at these two spec points. So the mechanisms for halogens to produce dihalogenoalkanes and hydrogen halides to produce halogenoalkanes. Okay, so we can get started. There's some essential vocabulary that you guys should already know for when we're talking about reaction mechanisms. Can someone tell me what the nice definition of an electrophile is? Yes, Aisha. Aisha, the major and minor product thing is Markovnikov, is the Markovnikov rules. Anybody got any ideas about what the nice definition for an electrophile is? Yeah, thanks, Yaz. So an electrophile is an electron pair acceptor. So if we were thinking about it sort of attacking a certain species, is the species it attacks electron rich or electron poor? Any ideas? So if an electrophile is going to attack something, is that thing going to be electron rich or electron deficient? Electron rich, yes, thank you. Thanks, Yaz. Thank you, Zara. So with our electrophile, we're going to be attacking things that are electron rich. And the way I want us to think about that is E for electrophile. And then if we have some kind of thing there with a lone pair of electrons, if I'm drawing a mechanism between my electrophile and the thing that it's attacking, the electron-rich thing that it's attacking, is my curly arrow going to go from the X to the E or from the E to the X? So if I'm trying to represent an electrophilic attack. Yeah, lag can't be helped, but we should be fine. Maybe the lag will go. Sometimes it sort of like minimizes as time goes on. Yeah, so we've got a lot of different answers in there. So when we're drawing curly arrows, because we've got so many different answers, I'm going to rephrase the question. When we draw a curly arrow, what are we actually representing? What does the curly arrow's direction represent? There's definitely a lag. Yeah, the movement of a pair of electrons. So we should be going from X to E, not to E to X. We should be going from the pair of electrons to the E, which means that our X could either be something that's delta negative, so like has a partial negative charge, or it could be actually charged. Either one, but even though it's an electrophilic attack, we need to be making sure we're drawing the arrow in the direction of the movement of electrons. Okay, so if we sort of do the same thing for a nucleophile, what is the definition of a nucleophile? Anybody got a nice definition of a nucleophile? Electron pair donor. Yeah, thank you. So we should have an electron pair donor. So in this case, are we attacking something that's electron rich or electron deficient? Yeah, there is a massive lag. Sorry, guys. I'm getting your comments a little bit later, but we will have to make do. Yeah, so we're going to be attacking things that are electron poor or electron deficient. So for this one, we should have the pair of electrons on the nucleophile itself. What could I explain in an example? We're going to be, as in, can I explain an example of what? Of an electron pair donor or something that's electron deficient? Anon. So we should be going our direction. What should our direction of attack be with our lone pairs? So should I be going from N to X this time or from X to N? Yeah, N to X, because again, I'm going in the direction of the electron transfer. And the electrons are on my nucleophile this time, which makes X either delta positive, so partial positively charged, or positively charged. An electron donor. So things like the oxygen in water or in an alcohol has a lone pair of electrons. So it's likely to donate that pair of electrons to something else. Just like your halogens also have lots of lone pairs of electrons. So they tend to be nucleophiles. They will, like things like in a substitution reaction, you have your halogen attacking something that's electron deficient. Cool, wicked. So the last thing we want to define now is addition. When we're talking about an addition reaction, what are we what do we mean? And I want this sort of in terms of pi bonds and sigma bonds. Any ideas? In terms of pi bonds and sigma bonds, what does addition mean? It is when you add an element to a molecule. Yeah, it is when you break a pi bond. Remember that a pi bond is sort of the double part of a double bond. It's the second bond on the double bond. So we want to break a pi bond, bake a pie, food on the brain. We want to break a pi bond. Yeah, thanks, Aisha, to form new sigma bonds. So Adam, addition reactions are in the AQA spec. You're not, so with addition, you're not expected to like write down this definition, but you should know that that's what's happening. So it is on the spec, Adam. It's just not sort of like one of the things like nucleophile or electrophile where you're going to be asked to define the term. Yes, so this is on all of the specs because you need to know what an addition reaction is. But it's just thinking of it in terms of what is actually happening. So you have one part of the one bond and the double bond breaking, and that allows you to form new sigma bonds. Yeah, exactly, Cameron. The sigma bond within the double bond stays unbroken. Okay, all right, we're going to move on to the actual. Yes, exactly, Hashimi. What are sigma bonds and pi bonds? Sigma bonds are your single bonds, pi bonds are your double bonds. Is everybody feeling comfortable with that? So pi bond means double, sigma bond means single. Everyone feeling okay to move forwards? Yes? No? Maybe? The lag is getting to me. Yes? No? I have no responses. I can't tell if it's because there's a lag. So we're going to see we're sort of going to see more of what that means when we actually draw the mechanism. So I think if you're like a little bit confused, then that will definitely help. All right. So the first thing we're going to look at is just the general reaction mechanism for electrophilic addition reactions. An electrophilic addition is when you have, or the sort of version you get in A level, the example that you're expected to learn, is when an alkene reacts with a halogen. That's the addition reaction that you learn. So in this case, we've got sort of two options for the electrophile in electrophilic addition reactions between halogens and alkenes. What are my two options for electrophiles, or just one of the options if you can only think of one? And I shall just sit here. Okay, wicked. Thank you, Aisha. So one example of an electrophile we could have is a diatomic halogen. So we could have Br2. What is the non-diatomic option? Or HBr? Thank you, Adam. Yeah. So these are, you can have any halogen here. The most common example used is bromine because bromine has some tests you can run with Br2 for this. So bromine is the most common one you'll see, but it can be any halogen. It could be Cl2 and HCl. It could be I2 and HI. Either is fine. Okay, so what I'm going to do is we're going to have a symmetrical alkane just to keep things simple for this first mechanism. So if I start with my diatomic bromine, if I start with BrBr, what do I need to make sure I draw on my bromine? What's the first thing that sort of happens? Any ideas? What's the first thing what is the first sort of thing I want to make sure I've got in my diagram before I even think about curly arrows? Yeah, my dipoles. So if I've got this bromine, the bromine closest to the alkene, what partial charge is it going to have? What partial charge is the bromine closest to the alkene going to have? Yeah, you're right, Blair. It's an instantaneous dipole. It's more of okay, so it's not an instantaneous dipole, it's an induced dipole, which is in the same sort of category, but it's the sort of electron density in the double bond that causes the dipole. So which one, is the closer one going to be electropositive or electronegative? Yeah, or otherwise called a temporary dipole. So if it induces a dipole in itself, vidit or vidit, that would be an instantaneous dipole rather than an induced one. Does anybody have any ideas? What part, I can't tell if this is still lag, what partial charge am I going to have on the closest bromine? Positive, yeah, thank you. I hope that wasn't lag, because if it was, it's a very long lag. So I have partial positive near to the alkene. And that's because on a double bond, of course, you've got two pairs of electrons. So that's a lot of electron density in one place. So an approaching bromine is likely to have an induced dipole created, where the electrons in the covalent bond are pushed towards the bromine furthest away. So we end up with a partial positive charge here. If we had HBr, we would have a permanent dipole, right? Because the bromine is more electronegative. So whichever we're using, the partial positive is next to the alkene, the partial negative is furthest away. But of course, we have an electrophile here. What is our, so if we have an electrophile, we definitely have to have the partial positive, because an electrophile is going to accept electrons, right? So if I draw my arrow, my curly arrow between my double bond and my partially positive species, where is my curly arrow going from and where is it going to, very specifically? And I'm just going to have to wait for the lag. Quite a long one. I'm still getting people saying dipoles. Goodness. Let's see. So which direction will my arrow be going in? Yeah, from the middle of the double bond to so you want it to the positive bromine, not the negative bromine. So we want to be going from directly from the double bond to the positive part, to the delta positive bromine, because of course if it's delta positive, it's going to want electrons. It's going to be attracted to them. And then when's my next? Yeah, Fazzy has already gotten there. I was going to say what is broken next. Or what's the next curly arrow? And the next curly arrow, of course, has to represent the breaking of the BR-BR bond. So we're going to end up going from the BR-BR bond to the delta negative bromine. Yeah, I think the lag is getting a bit better, actually. So I'm going to ask another question, and then if it happens straight away, we'll be all right. So if, at least it's free, yes, at least it's free. Okay, so what species am I going to be left with? I now have a bromine on my carbon, and I have a bromine sort of freely wandering around. What's the next kind of species called? Can I rub out the HBr? I will in a bit, but I want to sort of do the same thing for the HBr, so I will leave it up a bit. Any ideas for the next? What is the next? What's the product of this part? It is an alkane, but specifically it has a charge. It has another specific name. Yeah, carbocation. Thank you. So we're going to have a positive charge on one of the carbons, and we're not going to think about which carbon because this is a symmetrical molecule, so we're okay for now. So we should have a bromine on one side, and either, depending on whether we use Br2 or HBr, a Br minus for both, right? Because for both sides, we had the bromine released. So what's going to happen at this point? Where's my curly arrow going to go? Yeah, Stefani said intermediate carbocation, which is a good way of putting it. Any ideas? Where's my curly arrow going from my bromine? Yeah, that is where Markovnikov's rule comes in, but we don't need to because it is it's a symmetrical molecule. From the lone pair to the carbocation, perfect. All right, so at this point, we have our product. We either have a dibromine if we used Br2, or we have a singular bromoalkane. Is this going to get deleted? As in the webclass online? No, it's gonna stay on YouTube. Okay, perfect. Is everybody feeling comfortable? Because I'm going to move on to Markovnikov rules. Yeah, I'm going to move on to the minor and major product thing in just a second. But this one doesn't have a minor or a major because it's symmetrical. I mean, there's so much of a lag that I'm just kind of just going to assume that everybody's fine. And if I see any questions, I'll flick back. But I feel like you guys are going to get bored of just waiting for me to see what your responses are. Okay, so we're going to be looking at Markovnikov rules. You may not have heard them called Markovnikov rules. You may have just seen it as which one is the major, which one is the minor product. But this is what they're called, Markovnikov rules. So essentially, we just looked at a symmetrical alkene. So it didn't matter which side the first bromine was attached to. But when it's unsymmetrical, it does matter which way around it goes. And the whole idea is that we need to be forming the most stable carbocation. So I'm gonna draw a non-symmetrical. Yeah, Vanshika, they don't call it Markovnikov in AQA, I don't think. Right, so we have a non-symmetrical alkene. We have a propene this time. So we're going to there are two possible products with propene. There are two possible intermediates. Yes, you're right. Snare? I have no idea how to pronounce your name. Snare? Snare. Let me know how to pronounce that because I have no idea. Sorry. Okay. Cool. So we have two possible products, right? We have the product, if we're sort of attacking, I'm going to use HBr this time. If we're attacking HBr, we can either have the carbocation on the right-hand side. I can see lots of you have the correct answer already, but I'm still going to draw this out. We can either have it on the right-hand side, or we can have it on the left-hand side. So lots of people are saying that the stablest carbocation is the one with more positive inductive effects. Yes, you're right, Stefani. No, this isn't the cis-trans thing. This is sort of like which side is the hydrogen going to be on, but it will cause cis-trans isomerism in some cases. Do Markovnikov rules apply with elimination instead? Not unless there are two types of elimination, one that forms a carbocation as an intermediate and one that doesn't. So the one that does form a carbocation as an intermediate, Markovnikov rules often apply. So yes, I'm going to go back to Lucy's answer. Lucy's answer was that the hydrogen goes to the carbon atom with the most hydrogens, and a sort of an easier way of thinking about it is thinking about the way charge sits. So if something has a positive charge, that positive charge is going to be a lot more stable on the carbon that is attached to other carbons. The positive charge on the carbon that only has other hydrogens is very, very unstable. So the kind of rule that you need to remember is that alkyl groups, so any length of chain, the longer the chain, the better, are stabilizing. So in this case, is A or B going to be the major intermediate? Yeah, Tofumi has also got it. Major products will be the one with the most adjacent carbon. So is it going to be A or B that's my most yeah. So T-Boy says tertiary carbocations are more stable than secondary, which is more stable than primary. Yeah. So is it going to be A or B? Getting a few different answers. Which one is my most stable? Getting quite a few different answers. So I've got a few answers in now, and it's actually going to be B. So if you sort of look at the rule where alkyl groups, so longer chains are more stabilizing, are B, the carbocation, the positive charge is on a carbon that is attached to two other carbons. So that is most stable. So B is a secondary carbocation. If you're wondering how we come up with the term secondary, think of your alcohols. So if an alcohol, if an OH group is attached to a carbon that is attached to two other carbons, it's secondary, right? Whereas A, the carbocation, the charge is on a carbon that only has hydrogens and is attached to one carbon. So it's a primary carbocation, which is a lot less stable. So that's going to be our minor product, and B is going to be our major product. So well done, everybody that said B. And I hope that's making sense for people that are saying, people that said A. I hope that makes sense. Okay, so there's just an extra bit of language. There's some differences in exam board language. So OCR does not give a name to this effect, to the effect of sort of like being attached to more carbons will stabilize a positive charge. So OCR people, you don't need to remember any extra terminology. AQA, you need to remember that this is called the positive inductive effect. So that's for my AQA people. And I'm going to write down that it's for AQA. So AQA humans, that is called the positive inductive effect. Whereas my Edexcel humans, Edexcel likes to call it an electron releasing, because alkyl groups are electron releasing. And I don't understand why, because the actual effect is called the positive inductive effect. So I'm sorry, Edexcel people, you guys get the weird language choice, but make sure you remember the correct term for that. All right, how are we feeling? Because we're going to go ahead and do an exam question. If you're feeling fine. And I shall wait the 30 seconds to get your feedback on how you're feeling. I'll sip my coffee while it happens. It would be so much easier if we all had the same length of lag. What does the positive inductive effect mean exactly? The positive inductive effect means essentially the sort of longer, the more carbons you have, they sort of stabilize the positive charge by sort of not donating electrons, but they sort of, okay, think of it like you have a bunch of carbon bonds, and all of the electrons in each of the carbon bonds attached can sort of pull towards that carbon that is positively charged. And that's because carbon sort of has more electrons than hydrogen does, right? So what we call carbon, we call it sort of an electron donating group, but all of this is very much degree level. You don't actually need to be able to describe what the positive inductive effect means in electronic terms. You just need to know that the sort of more substituted a carbocation is with other carbons, the more stable it is. Yeah, it gets electron richer. The problem is it's like a reasonably complicated effect, and the sort of Y's aren't on the Y's aren't A level. They're sort of degree level. So if you do chemistry at degree, then go for it. Then you'll like learn that properly. But we don't really have, you don't really have the knowledge yet to understand inductive effects. Okay, I'm gonna move forwards because everybody seems fine. Mirzab said 5, but as that is not a number on here, I can't take it seriously. So we're gonna go ahead and do the exam question. So in an exam, if they said explain the positive inductive effect, you would say the more substituted carbocation is with alkyl groups, the more stable the positive charge is. That's all you need to know. All right. So I hope that makes sense, Aisha and Isha. Yes, we're going to do the exam question now. So the question says that but-1-ene reacts with a reagent to form HY to form a saturated compound. No, you don't need to know it's called Markovnikov. So suggest a reagent to form the HY which reacts with but-1-ene. So this is just any reagent. Yeah, so HBr. Anything else? So we want to be really going for sort of, yeah, you're right, Adele. So we've got HBr. Any other possible reagents we can think of? Remember, we're sort of thinking halogens. Got lots of HBRs. All right, I'm going to ask the second question while I wait to see the rest of your answers. But anything else apart from HBr? Yeah, HCl, Fassi, thank you. So we could have had HBr or HCl or HI, all of them are fine. All right. So the next part says to name and draw a mechanism for the reaction in part A, and that's kind of the subject of this entire web class. So you should really know what it is. What is the name of this mechanism? Electrophilic addition, yeah. Oh, does this mean the lag is slower, or are you guys sort of preempting my questions? Electrophilic addition. Yeah. Yeah, I think Charlie just preempted it, right? Hi, Fassi. Okay, so at this point, the first part is just the normal electrophilic addition mechanism, the one we just did. We don't really have to think. If you remember the mechanism, you're fine. So I'm going to draw out my but-1-ene. So it's 1. So it must be sort of, we must have our alkene group right at the end. And that's going to tell you something about where the carbocation forms. But the first thing we're going to do is just draw out the first stage that we've just covered. So I'm not going to ask you guys questions. So we're going to have our arrow going directly from the double bond to the hydrogen. And then we're going to have it going directly from the hydrogen Br bond to the bromine. And I cannot sort of state how important it is to make sure you draw those curly arrows exactly the way I've told you to. You will lose your marks if you, for example, draw the curly arrow from the hydrogen to the bromine instead of from the hydrogen bromine bond to the bromine, because electrons aren't coming from the hydrogen, they're coming from the hydrogen-bromine bond. So be really careful. Okay, cool, perfect. So the next thing I want to think about is my carbocation going to form on the side, on the left-hand side, on the left-hand carbon, or the right-hand carbon? Is it going to form on the left-hand carbon or the right-hand carbon? Any ideas? We answered before you asked the question. Yeah, that's useful. Can I do another web class on free radical substitution? Maybe. Left or right? Yeah, thanks, Fassi. So it's going to be on the right-hand side. And I'm sure lots of you have already answered. So yes, it's going to be on the right-hand side because according to our Markovnikov rules, the carbocation must be on the most substituted carbon, most substituted with other alkyl groups. If it's got other sort of like halogens, it doesn't count. So they have to be stuff that's going to sort of provide stability to a positive charge. Anything electronegative is not going to provide stability. So we have a positive charge there. And then of course we can have our bromine, our Br minus attack with its lone pair of electrons to our carbocation and form a lovely bromo alkane. All right, so the next part of the question is about isomers. So the question says, explain how 3 isomeric products are formed when HY reacts with but-1ene. So we kind of already know what 2 of the isomers are going to be, right? Because we've just spoken about Markovnikov rules. So we know that we're going to have a major and minor product based on where the carbocation forms. So the first thing we want to write down is what the name of the sort of the secondary product is going to be, the minor product. So what are we going to say? So what's our minor product? So if we have if our major product is sort of 2-bromo butane, what is our minor product going to be? So I'll let you guys, I don't know how many of you've already answered, but here we have our, oh, that is a dodgy arrow. Here we have a we have 2-bromobutane. Yeah, thank you, Charlie. Thank you, Snea, sorry, and Lucy. The minor product is we have a 1-bromobutane. All right, so that explains how we have 2 isomers, but not how we have 3 isomers. So what's the 3rd isomer? If we go back and look at this. Yeah, I did, sorry, thank you. I did miss a carbon. How do you know when the delta negative attacks the positive carbon? Does the arrow go to the positive sign or to the actual carbon? It goes to the actual carbon because the electrons are being transferred to the carbon itself. So remember that all the curly arrow does is show how electrons are moving. So you want to show where the electron is coming from and where it's going to. Cool. So we know we had the minor product, but why do we have a 3rd isomeric product? So this is like across our different topics. Can anyone think about looking at this molecule? What's special about it? Anybody got any ideas? If I don't see anything in the next sort of 20 seconds, I'm just going to tell you, because I don't know whether that means you don't know or whether it means that the lag has gotten serious. So it's not a stereoisomerism. The major and minor products are stereoisomers. It's not attacking a different carbon. It's not a dibromo. You're right, it's not symmetrical, but what does that mean isomerism-wise? What kind of isomerism are we missing? You guys are all sort of talking about sort of geometric. We're all talking about stereo, but there's another type of isomerism that we're all missing. Okay, I'm just going to tell you. Look at this. If you're looking at the product, the major product, you'll notice that it is substituted with 4 different groups. Thank you, Isha. Yeah, you're totally right. We have optical isomerism going on, right? This carbon has 4 different groups. It has a methyl group, it has an ethyl group, it has a hydrogen, and it has a bromine. And if something if the carbon is substituted with 4 different groups, then that means that it is chiral, and we have enantiomers. So if you haven't covered optical isomerism yet, it makes sense that you wouldn't think of it. If you have covered it, then you probably should have guessed. So we can say that the major product has enantiomers. So this is a good example of having to think about all of our different kinds of isomerism. When we're thinking about isomers, we should be thinking about structural isomerism, we should be thinking about cis-trans, EZ isomerism, and we should be thinking about optical isomerism as well. Okay, so this is actually a 3-mark question, right? So we need to do some explaining. So the thing that we want to explain is why the minor product, why we have a minor product. So the sort of way we explain it is sort of how it's formed. So we want to say the minor product is 1-bromobutane formed via a primary carbocation. And I know you guys already know that. I'm just giving you the wording. So it's formed. What does enantiomers mean? If you haven't studied optical isomerism yet, that won't make sense. If you have, it will make sense. So yes, they're like mirror images of each other, but don't worry about it. If you haven't studied it yet, you'll get there and then you'll know what I was talking about. Yes, it is about chirality, Messi. Would you need to include about polarized light? No, it's only 3 marks. It's only 3 marks, so you're right. Enantiomers are just mirror images of each other, but if you haven't studied it yet, you will get to it by the end of the year, don't worry. All right. So that sort of brings us to the end of the actual class. So what we're going to do is I'm going to sort of like do our little pitch for you guys about getting to sort of meet me and be taught by me in April. So that is the plan for the next sort of couple of minutes. So I'm just going to thank you guys, by the way, for sticking around to the end. I'm just going to show you guys our beautiful I cannot say words. So yes, perfect. All right, so I'm just gonna show you guys the bits and bobs about our seminars. I can't tell if you guys can see the seminar screen. I think you can. All right, so yes, I'll see you in the drop-in, Benshika. So the seminars are going to be happening in April, and essentially it is a crash course of all of the chemistry, or not all of the chemistry, of a lot of the tricky chemistry that you're going to need. We're going to be doing biology and physics and maths as well, but I'm a chemist, so I'm going to tell you about the chemistry. So for chemistry, it's on the 7th and the 8th of April. Some of the topics that you'll be doing is exam technique, equilibria, periodic table trends, organic reaction mechanisms, enthalpy change. And we also have on the 2nd day, we're going to be having sort of exam technique, energetics, transition metals, electrochemical cells, and organic synthesis. And it's just like a really good opportunity to crash course things before you start panicking your exams, and just to get things down pat. So that is it from me. If it's too expensive, T-Boy, there are some options. Maybe if you email us at seminars at snapprovise.co.uk, have a look and drop us an email if it's a bit too expensive for you. There might be some options, so try that out. It's not going to be 20 quid, but we can. Yes, it is expensive, but remember that we have to like actually rent lecture theatres at Imperial. We have to pay all of the staff. We have to prepare everything. This isn't government funded. You guys are so used to school, which is government funded, right? Education costs money to provide, so it has to cost money. I'm afraid, which I know you guys are not used to, but that is the deal. All right, thank you so much for coming to today's web class. We'll be back again on Thursday doing another tricky topic. Feel free to message us on Insta if you have other things that you would really like to do. The more people that suggest the topic, the more likely it is that we're going to do it on YouTube. If you're one of our ultimate subscribers, I will see you in 15 minutes for our drop-in session. Where is it? It's Imperial in London, so it's like South Kensington. All right. Bye, my lovelies. It was lovely to have you.